Welcome friends to this new lecture of soil science and technology, and we will start from the soil water energy concepts because we left there in the last lecture. So, we have discussed about the soil water energy concepts and what are the different forces which act on soil water in the vadose zone. We discussed about the vadose zone. Remember, the vadose zone is unsaturated zone above the zone of saturation. So, let us see what are the three models of water distribution. So, the first model you can see here, it is called water film thickness model, and it shows basically the thinner water films around particle. I mean, when these are the particles, so you see three different particles, and the thickness of the films of water films is continuously going down as we are moving from the first one to second one to third one. Obviously, as the thickness of the water film around the particles are going down, their energy or potential energy also decreasing. So, at the top, when the thickness of the water is quite high, obviously that will be in a higher energy state, and at the bottom when the water is drying out, and obviously the thickness is going down, that will be in lower energy state. So, obviously the water will move from this position higher energy state to lower energy state. The second model is called cylindrical tube model, and it basically shows the implication of different size of the pores in water distribution. So, you can see that this is the wettest condition and this is the intermediate condition, and finally, it is the dry condition. So, obviously, when the soil is getting dried, and the water will first move from these larger pores. This larger cylinder is basically basically indicating the larger pores, whereas the small cylinder is showing the smaller pores. So, when the water is so when we are drying the soil, the water will go away from this larger pores, and finally, when the larger pores are emptied, and then the water will finally go from the smaller pores. The final one, the final model is called irregular angular pore model, and it shows that irregular isolated pockets of water. So, you can see these are these are angular shaped pores, and in the angular shaped pores, if we had started if we start drying this soil, the first the first the water will evaporate from this middle portion, and these three corners will hold the water in higher tenacity, and as we further dry the water from this triangular pores, the water will, most of the water will evaporate. However, there will be some amount of water that will still left in these corners because of higher tenacity. So, these three models of water basically shows the principle through which the water distributes from one area of soil to another area. So, these basically governs soil water, this governs the pathway through which the soil water will move from one portion of the soil to another portion of soil. So, let us see what is soil water potential. So, to quantify potential energy state of a soil water, a reference state is needed. Remember that we need a reference state for quantify the potential energy of soil water, because whatever we will be expressing in terms of potential energy, that will eventually shows the total soil water potential. And this reference state is basically potential energy of pure water with no external forces acting on it at a reference pressure, that is 1 atmospheric pressure, reference temperature and reference elevation. So, if the water is present in a pool, that water which is present inside the pool is considered as a reference state with 0 potential energy, and soil water potential is then determined as potential energy per unit quantity of water relative to the reference potential of 0. So, the water which is present in this reference state are considered as a potential energy of 0, and whenever we are talking about soil water potential, it always determine the potential energy per unit quantity of water relative to that reference state. So, if we see this picture gives a broad overview of different soil water potential. Now, you can see this slide is showing basically potential energy level of pure water at standard reference state, which is taken as a 0. And obviously, here the potential energy of soil water at a higher elevation than that of the standard reference state. Suppose here, and this will form the gravitational potential, which is another important potential, and energy level is obviously higher than as a standard reference point positive. So, whenever we are going in this direction, energy level will be always positive, and below this reference state there will be osmotic potential. So, what is osmotic potential? Potential energy level of water containing salts and other solutes. We will discuss this later on, and as a result there will be negative there will be the energy level is lower than free pure water at reference point. So, it is negative in sign, and finally, here will be potential energy level of water attracted by soil solids or soil matrix, and we call it metric potential. This is also negative. So, you can see the manifestation of different potential like gravitational potential, osmotic potential, metric potential, and their relative position as compared to this pure or reference state, which is taken as a 0. The potential, remember that the potential at this reference stage is always taken as 0. So, the formal definition of soil water is total soil water potential is defined as the amount of work per unit quantity of pure water that must be done by external forces to transfer reversibly and isothermally and infinitesimally amount of water from the standard state to the soil at the point under consideration. So, since water in soil has various forces acting upon it, potential energy usually differs from point to point obviously, and hence it is potential energy is variable. When the potential energy is variable, this is the acting force through which water is moved from one portion of the soil to another portion of the soil. So, remember that potential is defined as it is a multiplication of force and distance. So, if the force is basically denotes by mg and the distance is by L. So, this is the final expression, where is rho w is basically the density of water and volume of and v is the volume and g is the gravitational acceleration and L is basically the distance. So, it is expressed in Newton per meter, and so this is the expression of general expression of potential. So, total soil water potential is basically as I have showed you in that last picture, it is basically combination of four different potential. One is gravitational potential, another is metric potential, then osmotic potential and hydrostatic potential, and it is basically expressed in terms of Newton per meter square. So, let us see them one by one. So, let us start with the gravitational potential. So, the force of gravity, when the force of gravity acts on soil water, it acts same as it does on any other body, and the attraction being towards the earth center, and the gravitational potential, which is psi z of soil water, may be expressed mathematically as psi g equal to g multiplied by h, where g is the gravitational acceleration and h is the height. So, you can see this is the water wheel, and obviously, the water will always try to move from this higher gravity to higher position to the lower position due to gravitational attraction, and obviously, the water at this high at this height will have higher potential energy than that of water here with lower potential energy. So, while water will always try to move from this higher elevation to lower elevation, and this is called gravitational potential. So, the second one is called pressure potential. Remember that the pressure potential is basically the combination of both hydrostatic and metric potential. Now, it basically includes the positive hydrostatic pressure due to the weight of overlying water in saturated soil and aquifers. We will discuss that later on, and the negative pressure due to the attractive forces between the water and the soil solids of the soil matrix. So, basically as the definition says, this is the first one shows the hydrostatic potential, and the second one shows the metric potential due to the soil matrix. Now, let us start with the hydrostatic potential. The hydrostatic pressure gives rise to what is often termed as hydrostatic potential, and basically we denote this by psi h. A component that is operational only for water in saturated zone below the water table. And generally when you are swimming into some swimming pool and going, sometime you go down into the swimming pool, you will see you will feel this hydrostatic potential in your eardrums. So, this hydrostatic potential is only only can be found at a saturated zone, only in the saturated zone below the water table. And metric potential is basically the attraction of water to solid surfaces give rise to metric potential, which is psi m, and remember that it is always negative because water attracted by the soil matrix has an energy state lower than that of pure water. As I have already showed you in this in the diagram, that the matrix potential and this osmotic potential is always negative, because then the water attracted by the soil matrix has an energy state which is lower than that of pure water, which is considered as 0. So, this picture gives a better understanding of the pressure potential considering both hydrostatic potential and metric potential. So, as you can see, the top of the saturated zone, so this is the water table, and the top of the saturated zone is termed as the so this is the top of the saturated zone, we call it water table, and above the water table the soil is unsaturated and it is subjected to the influence of metric potential, obviously due to the attraction of different soil matrices. And water below the water table is saturated soil is subjected to hydrostatic potential. So, hydrostatic potential is always positive, however, the metric potential is always negative, and metric potential is governed by the capillary rise. However, the rise may not be always linear, and sometime it may be irregular due to irrigation and other and different types of water inputs. So, basically what I try to convey is that the pressure potential is combining two different potential, one is hydrostatic potential, another is metric potential. Hydrostatic potential always can be found at a lower level, at a level below the water table, and it is always positive. However, the metric potential is always negative. Now, osmotic potential. The osmotic potential or psi O is attributable to the presence of both inorganic and organic substances dissolved in water. And remember that as water molecule cluster around the solutons or molecules, the freedom of movement of the water is reduced, or in other words the potential energy is also reduced. So, that is why osmotic potential is also negative, just like as metric potential. In case of metric potential, if you remember, it is basically due to the attraction of soil matrix to the water, and as a result the freeness of the water to move to any other place is restricted, and as a result their potential energy get decreased. So, so this is why the potential energy of the metric potential and the osmotic potential is always negative than that of the reference state. And the greater the concentration of the solutes, the more osmotic potential is lowered, and obviously water will tend to move to where its energy level will be lower, in this case obviously to the zone of higher solute concentration. So, water will always move from a zone which has got lower solute concentration to the zone which has got higher solute concentration, because higher solute concentration means lower osmotic potential, and as a result of that water will move from higher energy state to lower energy state. So, how you can express the soil water potential? So, soil water potential can be expressed in three different ways. One is potential per unit mass, another is potential per unit weight, another is potential per unit volume. So, potential per unit mass or mu is basically expressed in terms of joules per kg, and obviously it is multiplication of two terms, one is g, that is gravitational acceleration, and L, that is the length, and basically the because the water height I would say, and potential per unit weight, that is expressed in terms of H, is basically basically expressed in terms of L, that is head unit, and which is also equivalent height of water, as we have already covered in case of capillary movement of water. And finally, and most importantly, potential per unit volume. We will be using most this potential per unit volume, and we generally use this denote this as psi, and it is basically the multiplication of this rho w V G L and by V. So, we are getting rho w G L, and it is Newton per meter square, which is the water pressure units, and obviously the SI unit, the similar SI, the equivalent SI unit is called Pascal, as we denoted by PA, and generally we denote the soil water potential in terms of either kilopascal or bar. We will discuss this later on. So, basically you can see comparing all these three, that is a potential per unit mass and potential per unit weight and potential per unit volume, that we do not need to compute the soil water potential directly by computing the amount of work needed, but measure the soil water potential indirectly from pressure or water height measurements. So, you can see all of these contains this L component. So, if we can measure these components, we can basically compute the soil water potential. We do not need to compute the amount of work needed. So, expression of soil water potential, as we can see, we can express the soil water potential either height of unit column of water means centimeter, or in bars, or in potential or in kilopascal. So, remember that the SI unit kilopascal is equivalent to 0.01 bar. So, it is basically conversion from one form to another form. So, this curve is very much important, we call it water characteristic curve. So, in this water characteristic curve, it shows basically the relationship between the soil water potential and volume of soil water content, or volume of soil, volumetric soil water content or gravimetric soil water content. So, you can see in the x axis we are just plotting the soil water potential in log scale. Remember that in log scale both in bars and kilopascal. So, as we are going from minus 1 kilopascal to minus 100,000 kilopascal, we are basically drying the soil, as you know that. And similarly, from minus 0.01 bar to minus 1000 bar, we are drying the soil continuously. And in the y axis, we are putting either volume of water content, or we call it volumetric water content, or gravimetric water content, or we call it mass soil water content. So, you can see at a given soil water potential, the clay contained higher amount of water than that of coarse texture soil. This basically due to the higher tenacity of clay for water as compared to loam and sandy, because in case of clay the total porosity is quite high. As a result, the total the attraction of water by the clay is quite higher than that of sand and loam. However, you will not see in these curves, you will not see the abrupt bend, and it is very smooth, as you can see. This smoothness is basically shows the continuous distribution of pore spaces in the soil. So, there is no abrupt bend or break. Another important thing you can see that there is a dotted line which is basically showing the poorly aggregated soil, same soil with poor aggregation. So, soil structure also affects the shape of the soil water characteristic curve. This is soil water characteristic curve, by the way. I have written water characteristic curve, but it is a soil water characteristic curve. So, you can see in case of a well aggregated soil, which is denoted by this solid line, it contains more amount of total porosity. The total porosity is quite high in case of well aggregated soil than that of a poorly aggregated or compacted soil. So, as a result of more or higher total porosity, the amount of water or tenacity of that well aggregated soil for holding the water is quite high than that of poorly aggregated soil. So, as a result, at a given point the poorly aggregated and the well aggregated soil will contain more water. However, as we compact the soil, the proportion of the middle and small size pore increases in case of poorly aggregated soil as compared to well aggregated soil. So, that is why there is a change in shape. So, water is released differently from those poorly aggregated soils. So, this curve basically gives us the relationship of change in soil water potential, how change in soil water potential, or in other words how the soil water content vary from one type of texture and one type of structure to other types when we are continuously drying the soil. So, when we are drying the soil, based on the soil texture and structure, the water content varies. So, that basically is expressed through the soil water characteristic curve. Another important term is hysteresis. So, hysteresis is basically the relationship between soil water content and barometric potential and of a soil upon being dried and then reweighted. So, you can see again this hysteresis is basically showing the relationship between barometric potential and soil water content, and here we are we are denoting soil water content by theta, and so also barometric potential is given either in bar or kilopascal. So, you can see the relationship between the soil water content and barometric potential for a given soil when we are drying that soil is not similar for the same soil when we are reweighting it. So, there is a difference, and this difference occurs because of several factors. One is either non-uniformity of soil pores, entrapped air, and swelling and shrinking properties of the soil. So, let us start drying the soil. So, in case of why there is a higher moisture content in case of drying? So, you can see this is a drying phenomena, and large pore remains full because of capillary attraction in the narrow pores above. So, these are large pores and these are narrow pores. So, the capillary movement of water will push more water to this narrow pores. So, as a result large pores remain full, and this is called the ink bottle effect. And so, as a result there is higher moisture. However, when we are reweighting the soil, water is drawn up by the narrow pores but the capillary rise ceases when the pore widens suddenly. So, as a result of that, at a given metric potential, the water content in a drying soil will be always higher than that of the water content when we are reweighting the soil. So, this property of soil water is called hysteresis, and as the soil are weighted, remember that another factor, when the soil are weighted, some of the smaller pores are bypassed, leaving entrapped air that prevents the water penetration. So, this is another important aspect of this is another important reason for lower water content in the reweighting curve. So, this is called the hysteresis property of soil. So, we have discussed about the energy concepts of soil. So, let us discuss about different methods for measuring soil water content. So, we can broadly differentiate the methods of measuring soil water content into direct method and indirect method. So, direct method we will be discussing about the gravimetric method, also we will be discussing about the volumetric method of soil water content. However, indirect methods are needs to be calibrated for specific type of soil or specific type of conditions, and the indirect methods can be divided into chemical methods, thermal property method, acoustic methods, radiation technique and electrical property based methods. Radiation techniques are of two types, one is neutron scattering, another is gamma ray attenuation technique. Electrical properties based methods are divided into electrical conductance and dielectric constant. So, based on dielectric constant we use TDR or time domain reflectometry, we will discuss that in detail in the next lecture. And based on the electrical conductance, there are gypsum blocks, nylon blocks and changing conductance. So, all these are different methods for measuring soil water content. So, this slide gives you a snapshot of different methods which we use for measuring the soil water content, and in the next lecture we will try to discuss them one by one, and in the next lecture also we will be discussing about different methods, what are their drawbacks, what are their advantages. So, let us wrap up here, and from next class we will be starting discussing about different methods of soil water content, measuring soil water content in details. Thank you very much.